Okay, start. Okay, so hello everybody. so, so okay, it's all jury rigged. So it's a miracle it works, but it works.
I will just ask: is it just a sub point of a previously introduced topic that phenomenological quantum systems?
Okay, very good. So I'm using the titles to title sections and kind of numbers for you to ease your navigation through the source paper. Okay, the source paper is the right, because if you don't know, there is the through the website, through the
Theory.
yeah. If you go through the website of our of this lecture, right? Here is the paper, link to the paper. This whole the things I'm talking about, you can find them written down in this PDF. Okay. So basically, so this is the title. I'm using those same titles for ease of navigation. Okay. Yeah, because I can use the same numbering. Okay. Maybe I will. You know what? I will use the same numbering to make it even more. What?
Okay,
bad idea?
You can put a number in bracket of the corresponding.
Okay.
Let's vote.
Let us vote.
This issue
First, we should vote on the method of voting, and then on method of deciding.
White or black.
First, we have to choose.
White is for adding the number and black against, or vice versa.
Or in paper. Yeah? Okay. Is it visible dot?
I think we can vote on this.
Okay. Executive order. No voting. Okay. So last time we talked about the students locked in the basements, right? Mostly. Okay, but students gave us probability distributions, multi-time probability distributions that like quantify the phenomenology, right? So we use the notation, this vector-like notation to denote tuples, krotki in Polish, right? Yeah. So the superscript denotes which choice of the measuring device, right? Subscript denotes the corresponding time when the measurement with this device was deployed, and the arguments are the results read out from the device by the experimenter, right? And right, we talked about couple more things, about some more advanced theory of probability. Just basically, the point of this of more technical tangent was to point out that even though our experimenter gave us this whole family of this kind of probability distributions, but even though they are describing, some sequence of measurements done on certain physical system, the connections between probabilities with different timings, right? Different sequences of timings Although sometimes it might be intuitive that there should be some connection between those different distributions. Like from purely logical point of view, there is no reason for such relations. If those relations are present, they are, enforced by physics of the problem. So now that we have this language, how we will describe our experiments, now we want to proceed to analyze what we see. So the first observation I want to talk about today, and I call it. So the numbering also corresponds to the numbering in the paper. So we'll have. Let me change color. Okay, how do you change color? Here. Maybe blue. Blue is nice. So we have phenomenological observation 1, parenthesis, causality. So first couple observations would be, we want to establish those relations between sequences of measurements of differing lengths. Okay, and the causality. Maybe I will just write down the contents. So we have it worded like this. When a probability distribution describing the sequential measurement is marginalized over the latest entry in the sequence one obtains distribution corresponding to the shorter time sequence. So in formulas, this means that you take your probability distribution that let's say have n+1 elements, the sequence of length n+1. Okay, in our tuple notation. Marginalization, if you remember from last lecture, means that you sum up over the entries. You pick the argument and you sum up over all the entries. And here we talk specifically about the latest entry, so the one corresponding to the last measurement, which means you sum over n+1 belonging to over the whole spectrum, to all possible values. And when you do this marginalization, you get probability distribution corresponding to shorter sequence. Okay. I call it causality here, but this is the this is good first observation to talk about. However, I'm a little bit embarrassed here because I don't really have a good story about this, good explanation why it should be called causality. See, the story is you can find in a couple of places in literature where people talk about some causal structures in quantum mechanics. So this is kind of tangent to the our role play here, and they when they talk about those causal structures, you can translate it into this property of those probability.
So it doesn't. Just name.
It is I mean, there is some story behind this, but I don't understand it. And so at this point, this is only the name, but I'm sure there is something deeper. I'm just too dumb to figure out what it is. But so
This is relatively probability.
no. It's some the only thing I know is this causality, but it's not, in the sense of relativistic theory. But there is something I just don't understand it. I don't have a good explanation.
The result of measurement in Tn plus 1 is a function of.
I don't know what it means, really. I tried to rotate it in my head in a couple of ways.
Is there like some relation between probabilities? Or what if we replace fn plus 1 by some f which is in the middle of this?
You see, this is specifically about the last one, right? Because there is a follow-up, the follow-up observation. It's like, okay, we check this for, if you remember, on the last lecture, I was talking about this marginalization as an example, right? That the intuitive expectation would be that if you marginalize over one of the entries, you should obtain the probability corresponding to the shorter entry, right? Like intuitive expectation. And I said, even though it is intuitive for some, in a moment I will explain why it should be intuitive, even if you don't know that it's intuitive for you, it is intuitive for you.
Future action for future does not affect the past. It's independent. Future should not affect past, right? This is the state.
I mean, I think this is what it tries to convey, but I don't know why this kind of relation conveys this.
But in the probability theory, when you look at the probability, look at probability distribution, if you marginalize over one of variables, you always get the probability distribution.
Yes, you get some probability distribution. Yeah, but
this is a specific probability,
yeah,
a specific event, but maybe
yes,
it results from the fact that there is this probability distribution defined on the space of all possible events.
I don't know. I mean, this is something about future and past and causal structure. I'm sorry, I don't have a really nice story. But
Sufficient. That's necessary.
I don't know if this is like necessary or sufficient for causal structure. I don't know what causal structures are actually. This is like the people they write about it, they use this kind of language. I mean, there are like two people who write about this, and they completely different contexts.
But the conditional probability.
I was trying to think about this in this kind of
one, and then you say, okay, the probability of having some results in the step n+1 conditioned on the results that and previous steps you got this in this sense maybe.
So it's like if I create, so this is we are still in a tangent right now. Okay, so if you don't know what conditional probabilities are, don't worry, we will talk about it later. But so Mariusz is so you are suggesting that maybe if I create this kind of conditional probability, right? N plus 1 Fn, right? Which is by definition, this is like bias rule, which is N plus 1. So you take the ratio of joint probabilities and the shorter one. Right? And but why summing over the latest entry should, I just don't know how, I just don't understand this. Yeah.
You said that's the observation. So
Yeah, yes.
observation.
So, okay, that's good. So this will, Emilia is asking about our modulus operandi, what we are doing. In what sense this is an observation? So it's so those probability distributions, right? Those are phenomenological quantities in the sense that they have been obtained from experiments, right? The students measured stuff, they got the whole, the bunch of data, and they estimate those probabilities from this data. So it's as close to being directly obtained from experiment as possible, right? So now we take those functions, they supply us with all those functions, tabularized, we can do whatever we want with them. So whenever we check something on those, we take and marginalize this probability, right? And we discover that when you marginalize over the latest one, it actually equals the probability obtained where you did sequence of measurements with one less measurement. So you are taking two phenomenological quantities and you are, looking what are their relations. In this sense, it's observation.
Examples of such observation from experiments, or you just somehow imagine that it should look like that for some reasons.
Okay, as you imagine, I'm which alternatives? Yeah, I mean, we talked with Fata about this a couple of times, but I still, there is a wide causality. I still don't really feel I understand it. But sorry, I got distracted. So example of experiment. Okay, so as you can imagine, it's not like I really have my student who's doing all the measurements, right? So it's not like so this observation is equivalent to stating that if you would take any quantum system and you would do all those measurements on it, this is what you would always get. Okay, so any example would satisfy this observation. This is what I'm saying. Okay? And I haven't done all those experiments, obviously, but I also am role-playing someone who doesn't know anything about quantum mechanics, right? So in reality, results of those experiments I'm talking about here, I know how to calculate those relations. I know the formulas behind it. I'm just pretending I don't know. Okay, so I'm not doing those experiments in my basement, obviously, right? I can simulate experiments using standard formalism of quantum mechanics, and then pretend that, in principle, you could obtain all this from experiments. Okay, do you see what I'm doing here? Is it acceptable? Because we know that quantum, if we drop the role play for a bit, we know that quantum mechanics is a very successful theory, right? The predictions for experiments, at least those predictions that can be, easily without any problems described with the standard formalism, right? So we know that they are agree with real experiments very, very well, right? Okay. We know that quantum mechanics, standard quantum mechanics, how it's formulated, is a very successful theory confirmed by experiments, many experiments done over hundred over the last century. So we don't really have to do many experiments on our own. We can just use the fact that we know that quantum mechanics, standard quantum mechanics, is good in predicting experiments, right? Am I clear here? Is it okay? So if you don't know quantum mechanics, you're listening to this and you're not fluent in standard quantum mechanics, okay, just pretend that we actually did all the experiments. But if you have some experience with quantum mechanics, we can check all those observations by doing we can just calculate them and show why it works. So as a tangent, another tangent on tangent, if you want to explain using standard formalism quantum mechanics this causality, we can just write down the probabilities, right? So if you recall this kind of probability distribution that describes sequential measurement. So we talked about it on the second lecture. There's a formula for this. It's like trace, right? And there is a product of projection operators corresponding to observables labeled by those capital F in Heisenberg picture. So also labeled by T. Again, this is just for someone who already knows quantum. If you don't know quantum, you can forget about this. Okay, it's initial condition. T1, T1. Okay, and now notice that trace has cyclical property. Okay, so I can take this projector and move it here. Okay, right, and projectors are how do you call it? It's not nilpotent, it's idempotent, right? So this equals this Fn, okay, right? And now when I take this and sum over Fn, the last entry, right? So I get trace, and I have sum over Fn and capital Fn n minus 1, n minus 1, so on, Tn minus 1, n minus 1. Right, we use the cyclic property to move this guy here and consume it, and this is identity, right?
It also is obvious from this conditional problem.
It's kind of because it has to be normalized, right?
Yeah. The concept of trace as a particular definition of probability, I think that the formula above is more general. The proof above is more general.
Because the sum
there is some trace, whatever. That if you multiply it by Fn first of all by this, then
You think
Not-
this
not
this is
some test.
this is a good story for this? But still, well,
But it's not like what you said, the sum is wrong. First, you have to write what is P Fn plus one Tn plus one. It is product of P at time Tn times
I mean,
probability of obtaining n plus one, provided that you obtain F. And then when you sum
Yeah.
this,
so this is conditional probability is a probability, right? So it has to be normalized, right? And conditional probability is given, this conditional probability is given by this. So it's normalized. So when I sum over this last argument, which equals summing over the, right? This should be one. So sum of marginalized n plus one divided by Fn equals one. So they have to be equal, right? But is this it? What kind of,
so conditional, it's always like that. When you have to, if you have probability in many dimensions, and you have to generate something from the distribution, you can have one particular distribution, whatever, and choose something.
okay,
And second is
but okay, but
probability of
this is not,
whatever
this is not,
in
this,
the n plus one step. It is probability that you get something, probability that you get this, and then you so
it's not, you know what,
but this is just
let's go, I think I will have counter argument to that. But it sounds very plausible, but I think I can get a counter argument to this. Okay, so Emilia, is this like satisfactory?
Actually, that's Mariusz. That it is like conditional probability, provided. that
Okay,
before-
but explanation of the, you know, the phenomenology.
But I want to say that probability of having n
Sorry.
plus one results is
I-
always probability
different-
of having n
Yeah.
results, and then the last result provided the
Yes,
previous one.
yes, exactly.
This is not the, it cannot be for any intermediate, but for the last, yes.
Yes, yes.
So
Provided
this is
that
just, I
you
think,
know
the
it's-
trivial statement in probability theory.
Okay. Or if you, because,
Provided that
you know,
before-
because I could make a conditional probability where I like pick one of the intermediate, right? This would be my conditioned on the past and future.
Yeah, this is not good. For intermediate, it is not true. I can
Okay.
use this argument, but I think.
Okay, if you amend with that, okay, maybe that is the explanation.
Because that's how I imagine. I already have some and trajectory.
So that
Then I condition to this, I am talking what, and then if I take anything, so this is the question, what is the probability of getting anything in the n plus one step, provided that you've got something in n steps? It means this is just probability of what you got in n steps.
So if this is correct interpretation, so we just discovered something that any theory would have this property. I mean, without tachyons.
Not be defined as a trace over
Okay.
something, and you use this
Any
property that you can.
any theory without tachyons would have this property, this causality, right?
In theory, what?
Any theory without tachyons, right? So the causality. I mean, this is how people called it.
So if, because I think that the only relation to causality is something that you said, that what you will get in the future
Cannot depends on only on past.
on what you had in the past. That's
Yeah.
times
Mhm.
probability of getting this. So that's why it is causality, because if you want to have the probability for the next step, you have to know probability for the past, not for. And then conditioned on what happened in the past, you have probability of getting final result.
I have to think about it more, but this is
because it depends on previous argument,
but not future.
So,
So you see, we just discovered, I guess, that it's any, if we were testing any theory, so the student was measuring
because
any system that doesn't have tachyons in it. Okay, so the future cannot interfere in past. We would. This is what the observation one, because this is what we would get. It's not a special feature of quantum mechanics. It's of any causal theory.
you know,
In sense that past affects future, but not future past.
You had n particle probability distribution in the position space.
Okay.
And then you want to find one representative, want to generate something out of this distribution. So the simplest way, but not only, is to find reduced one particle distribution to summarize.
Yeah. Okay.
And then to pick up the first particle from one particle distribution, then to have two particle distribution.
Yeah. Okay.
Marginalize over, and then to find and then you pick up the second particle from this two particle from the conditional probability distribution, provided that you have this one, and then you always do your random choice from one particle distribution which is similar, and then you multiply it well, and then you show that n particle distribution in fact is probability of finding one particle of obtaining F1 times conditional probability of obtaining F2 provided that you have F1 times conditional probability of obtaining F3 provided that you obtain F1 and F2, etc., etc. So this n particle distribution can be always written as a product of multiple.
Well, but that's but here is more narrow, right? This is like, because it's time is involved here, right? This is a
product is you are specifically different condition because you also have independence.
Yeah.
Independence of the event, but if you don't include independence, you cannot actually take product. You just, but in this condition is actually general condition in our world, I guess.
Yeah. Okay, so I learned a couple of things. Thanks, guys, for explaining it a little bit to me. So we see, we just analyzed some phenomenology and we came up with some general statements.
No, so I call it observation because it's like properties of probability distribution.
Yeah, we observe this property. It comes from phenomenological objects. It's a property of phenomenological objects. So it's you don't. No, no. It's an observation because it hasn't been derived from any principle, fundamental. We just noticed this property by examining the phenomenological probability distributions we got from experiment. So it's observation. It's not lemma. It's not theorem. It's an observation. It's not proposition. It's an observation. We noticed.
It's already observed because you by projection operator, each actually time slide you observe.
No. It's not observation in the sense of measurement. It's we are making observation about those probability distributions, about the structure. Okay. Oh my God, you're grilling me over the nomenclature so hard. Well, but there will be more that are not. Yeah, I mean, all experiments are described by those probability distributions, okay? Yeah, because every experiment corresponds to some probability distribution. Okay? I mean, if you think about this is yeah, and all experiments are described by probability like this.
Okay.
Okay. So
Just have a point about this because I think we understand that what we see here is that the measurement simply, maybe I'm referring a bit to my wider knowledge of quantum mechanics, which I should.
yeah, you should.
But we see that simply measurement affects things after the measurement. But this is our educated knowledge already. And what we saw at first instance is just, okay, so there is something all about this measurement, because if we just, as you said, abstract from the summing up, we called it, marginalize with respect to one of those measurements, you do not get a probability distributions like without this measurement. So what you normally require from the measurement in standard classical mechanics that is just a picking the values from of some observables at some point, and it completely does nothing to the system. Here it's not more true. So
don't spoil it. It will be second observation.
Okay, but
we are now
just,
getting
just
to
one
this.
step down. That okay. So if it is not true, then at least the causality maybe should be preserved, but it's not necessarily. I don't know. Maybe I have a faulty intuition, but if such a thing like measurement is no more non-destructive, I don't. The fact that I should ask if the causality is still held. If it is so that things affect things afterwards.
What is the discussion? Because I missed it somehow. Maybe I was thinking about something else.
I mean, Hubert is like trying to get into the role of someone who doesn't remember anything about quantum mechanics, and it's not easy.
It's no one about mechanics.
Yeah, exactly. But but he knows there is, right? So,
We are measuring the quantum mechanical system, and we already see it.
but this particular observation, yes, exactly. This applies to everything.
But we believe here that we measure fundamental things, that we do not have such a kind of measurement that simply disturbs our system mechanically.
Hubert,
not said. The only
This
thing which was
disturbing-
results are probabilistic. The only thing which might think, oh, in classical mechanics, you say that in principle you have everything deterministic, so probability doesn't make any sense. But if you say that you have statistical mechanics or something and your results are probabilistic, so this is just true for any probabilistic theory. That's it.
For any,
How this theory
and
of
any
probability
theory can be written in terms of
some
probability.
elementary events which are F1, F2, blah, blah, blah. So this is the space of all processes. And they are ordered. So this is.
Let's move on so that I can address Hubert's, question, comments also. So the second observation. So we did marginalization over the latest one. We had this very beautiful discussion about why it's reflecting a causal structure of the theory. And now let's marginalize over any other, right?
Discussion gave explanation why it is called causality. I think that now it is obvious. The general property of the probability theory that final result depends on the probability of the previous.
So we go, okay, so let's do the marginalization over.
It's general for physical worlds, not for probability.
For any probability theory.
Okay, but
No.
theories you don't have time.
But it can be another.
But it was not summation over time. It was just.
No,
Yeah, but it was time.
marginalization over the latest. That's very specific because now, okay, let's marginalize over not the latest, somewhere mid sequence. So I have it written down as the marginalization over the readouts mid-sequence does not generally result in a distribution for a shorter sequence. Distribution for a shorter sequence. So in terms of formulas, the way I will, maybe it will look very mysterious. The way I like to write it, there will be reasons for this. So let's say we pick a measurement done at time tj to be the one we marginalize over. Okay. Where we write this like this. So now let me cross out this guy. So this is a probability for the sequence where without j, okay? Minus sum over j. So this is the marginalization happening. PFM So we take probability of sequence where there are n measurements. We marginalize over fj of the one made mid-sequence at time tj. And we want to see if it's equal probability where there was no measurement at tj. And our observation is that this is not zero. Okay. I wrote it. It will later on. It will be clear why I wrote it like this, because there is. So we don't have the same kind of reduction as in causality here. There is some reminder. Okay, there's something else. There's some additional thing. So, you know how this connects to causality and stuff like that. I'm not perfectly sure. But this is like the fundamental observation that you can make here, because I would say that if you see this kind of property, I would say that you immediately know you're not dealing with classical system or classical theory. And to understand why, let me.
There is no classical disturbance of the system.
No,
but it is not so that okay, my measuring in principle disturbs the system classically, but
no,
assume that we do not do it.
Don't, you're thinking about some. I will address this. Okay, this is. I will address it in a second. But to explain why this is this thing here, this inconsistency, as I call it, why is it so pivotal? We have to make it's kind of tangent, but not really. I have to explain a bit about stochastic processes here, okay? But I will do it after the break, because I think it's a good place to make a break, because it's we are an hour in. Okay, so let's take a break. We had our break. I hope we rested a bit. So now let us continue with this stuff. So I think last time we figured out the causality pretty well. I feel good about it. So it's so So I think that this property is actually, this is like a universal, any theory, any measurements would display this kind of property, unless you future can influence past in some way. If not, then, you know, if only if past influences future, this property will always hold. Okay, so why this thing is kind of pivotal? Okay, so to explain what is the meaning of this, why you even want to check this property, we have to unfortunately talk a little bit about theory of stochastic processes. So this is kind of tangent, kind of not tangent, because this is, you know, integral part of this whole reasoning. But let's say, let's entitle this, switch to black. Some theory of stochastic processes. I assure you this will be very interesting. Okay, it's not just math. So you are used to probability distributions, right? You have your function, non-negative function of some stochastic variable, right? It's greater than 0, normalized over x equals 1, right? You can have function of single variable, you can have many variables like x, y, z, for example, right? Sum over all of them, it's normalized to identity. Of course, those multi-time probabilities we are talking about here are just example of this kind of multivariate probability distributions. But there is, you can progress this further. Okay, so these are distributions on the space of numbers, but you can consider probability distribution on space of whole functions. Okay, not just numbers, but whole functions. So we have a probability distribution that is a functional. That is, functional is a function that takes other functions as its argument. And functionals, I would denote them with, I would try to calligraphic letter. So this is supposed to be calligraphic P, okay? And the arguments, it will take arguments in square brackets, okay? So if I write something like this, this means that this is a function. So let's say it's a function from some parameter t to x of t, okay? Okay. And it is customary to also write, like you have a probability distribution for a continuous variable, right? So you, if x is, for example, a real line or something like that, you also write, you know, differential next to it, right? So to remember that this is a probability distribution for continuous variable, so it's customary to also write differential, but functional differential. Okay. Also, this is one of the conventions for notation, which means that you can do calculate some integrals, functional integrals with this distribution. These are all very scary things. Okay, you don't usually attempt to actually calculate those integrals because that would be insanity. But like formally, mathematically speaking, this all well and good things that you can talk about. So function of other functions is there's nothing wrong about it. It's just generalization of what we are used to. So if you have this probability distribution on the space of all functions, so it's positive and it's normalized in the sense that you actually do the integration, which is, again, technically it's some kind of nightmare how to actually execute this integral, but as an inscription, it's all good. Okay, so when you're talking about, you have probability distributions for numbers, you're talking about stochastic variables or random variables. You have probability distribution for functions, you are talking about stochastic processes, okay? And the arguments, so this function here is then would be a trajectory of a process. Trajectory of a process.
But what is process?
A process, okay, if you want formal definition.
Yes.
Okay,
Because then I don't know what is trajectory of what.
okay, let's do it. Okay, so
Is any sequence
let's start with stochastic variables, okay, so numbers. So formally, stochastic variable, it's not, if you have probability distribution for a stochastic variable, this is not stochastic variable. This argument is not stochastic variable, okay? Stochastic variable is a formally, so capital X, is a map from some space of random events to numbers, okay? So, for example, if your stochastic variable would represent a coin toss or something like that, okay, tossing a coin. So your random events would be, you got head, you got tail, right? So let's say head, tail, head or tails, heads, tails, right? And the mapping would be the head. When you obtain head in your, you toss a coin, you get head, you assign it some number, let's say x, h, with tail x, t, okay? And then probability distribution for this stochastic variable would be, is a function on this space, okay? So it assigns some probability to xh. So if it was per coin, that would be 1/2, for example, right? xt, that would be also 1/2, and so on. So stochastic variable is like a why is it invented? So if you want to do some math, standard math, with something that represents some randomness, then you can use the stochastic variable, so this guy here, as a placeholder. Okay, you just treat it as a normal number in your calculations, but until you do the coin toss, its value is undefined. Okay, when you do the coin toss, you get your results. It transmutes into the respective number. Okay, so it's like, so stochastic variable is this mapping of some abstract random events to concrete numbers. All right, probability distribution is a distribution on the image of this stochastic variable. So on the numbers the variable assigns to random events. Okay, so it's like you daisy chaining the abstractness to numbers. So now stochastic process is also a map. It's like this. And it is a map from random events to functions. Okay? So so you could have your random events could be very simple. Some also head tails, and it would map to some function, okay? Some function of time, some trajectory, okay? Xt. And so on, all right?
What is the sequence of random numbers?
Stochastic process is a map between random events and functions. Usually functions of time. This is how typically it is used. Although just not numbers but whole functions, right? So you could imagine, yeah. So this is like just straightforward generalization. We go from get random things to numbers, random things to functions. You could imagine random event to matrices. You would have stochastic matrix then. So
if I do something extremely stupid, I have two random events, head and tail, and I will assign sine function of t to head and cosine to tail. So I can plot it independently on the result. I can plot sine of t and cosine of t. So it will be my stochastic process, or it will be just jumping between sine and cosine. The sequence that you enumerate by time.
What you would see, what we will plot depends on what you were trying to do. If you, for example,
number, but I can assign function. So whatever I assign function, sine.
Yeah.
And then x of t is what? Sine or cosine?
X of t. I mean, look. If you write, let's say, integral of x of t, something like this, for example, this will be something. You essentially create new stochastic process. No, that will be actually stochastic variable after you integrate. This is you take one stochastic process and turn it into some others. So this is example of stochastic process. This.
No, this is sine and cosine. And x of t is equal to
x of t. So that would be xh of t, right? You pick it to be this, and this x of t. I don't know what you want from me. This is an example of some stochastic process.
The only thing I can imagine, using this head, this flipping a coin, that I am repeating this experiment with many times, and I number this sequence that I obtained, and then I have some random sequence, and then I will say this is my stochastic process. Because when I assign function independently on anything, that doesn't mean that I can plot sine function, assuming that t starts at midnight, and then cosine.
Most likely,
I say this is my random process.
Most likely, this random event.
To select numbers.
This random event, it's usually it's not just a coin toss, right? Where it's a probability of getting head is 1/2, probability of getting tails is also 1/2, right? It could be some different distribution. So if you, for example, want to like average trajectory, right? Average trajectory, which would have.
I want to have one example of stochastic process.
Stochastic process is a mapping of random events to functions, like random variable.
Map is a kind of function. So you say that.
No. Map is not functional.
It is a function defined on the space of
probability distribution on the space of those, the functions that your process maps to is a functional. Okay, so process, abstractly speaking, formally speaking, is some nebulous random event like coin toss or whatever.
So I should write sine squared and cosine squared to make the probability. No, not necessarily. Okay, yeah.
No.
So this is probability P that I have.
You're talking about probability.
Could you give us some immediate example to understand better?
Yes. 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 Imagine you have a classical pendulum or something on a spring. Some weight on the spring. Okay. It has you can solve the equations of motion to get a trajectory for the motion of the weight on the spring, right? It could actually be sine of cosine of t, right? And if you pick one initial condition, one specific initial condition, so to this initial condition, you assign the solution, sine of t.
In Wikipedia, they say the probability theory and related fields are stochastic for random process is a mathematical object usually defined as a family of random variables in a probability space.
You can say it like that also.
Because for me, this is simple. I take the sequence of numbers, and this is stochastic process. But you call it this as a function.
I mean, you asked me what I didn't want to talk about it, but you tried.
Definition.
Look, the solution to the weight on the pendulum can be viewed as a stochastic process. Very simple process, because if you have only one, let's say one initial condition, there is one solution, one trajectory. So it is a very simple stochastic process that has only, that's basically a delta. So if there is only one solution, you would have like probability of x, that would be a delta of x minus functional delta of the solution. So let's say sine of, let's say sine of t, whatever. Okay. That would be very simple. Now you can make it more complicated. Let's say the initial conditions have some probability distribution. For each condition, you would have some trajectory. That would give you a little bit more complicated stochastic process. Okay, where the probability distribution would be, in that case, so if we say that this, so let's call it the solution of t on some initial condition in it, okay, and some probability distribution of x in it. That would be a classical system represented in terms of stochastic process. This very simple stochastic process. Of course, you can sometimes or very often, and this is how usually people use stochastic processes, they want to describe noise, right? So something that, you know, when you plot noise, it's in some wiggly line, and this usually can be represented by some stochastic process. So essentially, you have trajectories that you know, that are some telegraph noise switching between two values, right, at some random moments. But the randomness of the noise is somehow it's not the point of the stochastic process. More, the point are trajectories. Okay, that you can, whenever you have some description that involves trajectories, like for example in classical systems, you already have a stochastic process. It can be deterministic stochastic process where there is no randomness whatsoever, but it can be also a process where there is some randomness, you know, some Brownian motion, for example, stuff like that. The point is that you are upgrading from numbers like with stochastic variables to whole trajectories. Okay, so if you imagine your process, you are randomly picking some trajectory with some probability distribution. Okay, and this can describe motion of a spring on the on some pebble, Brownian motion. So it's like a particle in the fluid or something. It can be a planet revolving around its star. It can be electromagnetic field, whatever. You know, it's a.
So the time is essential. There is a parameter that.
Typically, people use it and think of it as there's parameter, which it's time, interpreted as a time. But it could be whatever. You know, you could. I lost my.
But I think that you have to have some order in this parameter. It cannot be.
Yes. The ordering is kind of important, but it can be. You can have.
Three numbers.
So you could have a particle. You could describe it as the process could represent a trajectory of the position, so how position changes in time of some particle. But equally well, you could represent like a mass density of this particle, which would be a field. So something that depends on time and position. So you could represent electromagnetic field as a vector stochastic process that, you know, it depends on time and position. And you have then you have the probability distribution on configurations of this field. What I'm trying to say that with the idea of processes, it's very universal. You can describe many things in this kind of formulation. Specifically, any classical theory can be like reformulated in this language. Okay. Classical mechanics, classical electrodynamics can be reformulated like that. Whatever you think about, I guarantee you can rewrite it as that there is some probability distribution in the space of some trajectories, which can be trajectories that are functions of time or fields, so time and space and whatever else you need. Okay.
Okay, but things are probabilistic, so are not probabilistic.
Randomness is
okay.
Look, randomness is optional. Randomness is optional here.
Okay.
Right?
But it's still true.
You could think of so let's say you have your classical like planet revolving around sun, whatever, very simple deterministic system. So then you can like rewrite it in this language, and then this probability, this functional P, would then act as a filter. Okay, so only all impossible trajectories. So when instead of orbiting around the sun, your planet would do some weird shapes. It would have this probability 0 for that. Okay.
Okay, I see now.
But the point is that you can reformulate it like that always. Okay. It's not always practical, but you can always do it. At least in case of like the theories, classical theories we know. And there are immediately a lot of consequences that coming from this kind of description. One of those consequences is how if your system or whatever is described in this language of processes, then the measurements also have to be described in a very specific way. Because if you think about it, you have your observable represented by a stochastic process, okay? Then when you're doing measurements, you are asking, okay, so what is the probability that my observable had some value x1 at time t1, and value x2 at time t2, and value x3 at time t3, and so on, okay? So you are basically asking what is the probability that the trajectories of my system will satisfy some constraint. Okay.
I had this question and I am not sure if the answer about this time t, because we have these events, and then we have some function which assigns some numbers to the events. And you said that there is this function of t. They ask if it is time or not. And you said it can be time and position, whatever. But time you can order. If you have real number, one you can order. But if you have points so my question is, I can add position. They are position on a plane at a given time. Is it important that there is an order or not? Because let us remove time, I will use electromagnetic field, whatever position X.
This depends on what.
So I'm talking for stochastic process. If order you have function.
You could,
because I can define function on a plane, yes, and then I don't have any order.
If you think in this general way about stochastic process, it's just some distribution on the space of functions. Okay, fields, trajectories.
But you very often say about this time.
Yeah, often most
that this is extremely important.
Most of the time. See, most of the time.
Time has a lot.
Time is significant, and like causality is significant. So this shapes what kind of those distributions are. What is the shape of the distribution?
So as
right?
long as we don't add physics, we don't need
Yeah. Yes.
When we start to use this for some.
Yes. Exactly. This is very good way to put it.
But this was general, even without adding. The order was important.
Well, it was because So I'm trying to get to connect this with what we.
Yeah, because the order was important, and
yes.
To say that we have the stochastic process, and still I want to know if. So for general definition of stochastic process, I can define the stochastic process on a plane without.
Yeah, if you think about stochastic process.
I don't, because that is a function of t. This t was one.
Well, that was an example. You could have
a stationary distribution.
Let's say you have P that takes arguments.
X.
Let's call it E, and E is a function from T R to some R3. Okay, this is a function, space of functions, so the configurations of electric field, let's say, that would be. So that is a space of your functions, and you can have a probability distribution all over the space. That would be a stochastic process. You could eliminate time from this. So static scenario, that would still be a stochastic process in this very general way of thinking. If you did something like this for stochastic variables, stochastic variables are too simple to survive doing something like this. But if you think about stochastic process, when they describe noise, is just one example of the one use case for this more general framework of using describe your systems in terms of some configurations, trajectories, or whatever, which could, for example, represent some observables, and which trajectories are possible or not possible is determined by this distribution, which can be interpreted as probability distribution, but doesn't have to be.
On this function, the probability of
yes.
And this say that this is stochastic process. The definition of this probability distribution of function.
Yes. So this is like.
So why we are having new name to something which is probability for this probability density? Why we call it?
Because it's on the space of functions. Yeah, it could involve
another name. But I don't see needed, but it is confusing for me to give a name to something which is probability
know,
density
mostly-
on some functions.
mostly we-
functions. To call this probability density a stochastic process.
I mean, you
that's
can-
the names.
you can you know, you can call it just.
I have a name, probability density.
I mean, it is probability distribution, yeah, but the fact that this probability is over space of functions, it's kind of, it behaves, it has its own menagerie of quirks in respect to.
Probability theory, say some, we never say that this
Look.
is defined in numbers. When you open any textbook on probability, you say that you have
Well,
sets, open sets.
This is not true. If you are learning probability or theory through as a measure theory, which so advanced math that we are like touched upon previously, then there is no need to make a distinction. But typically, when people Gaussian distribution and stuff, that's why there is different name, So you entered a different domain, okay?
So
And
for the purpose of this.
and
I can
in
see
particular,
the process probability distribution on the function.
yes, this is good. You don't need to know anything else, but there is but you can reduce it to standard probability distributions on the space of numbers, which we will do now. Because like I said, okay, so measure. Let's say that your process represents observable, okay, something that can be measured. So if you want to describe a sequential measurement of this observable, right? So you want to get this probability, multi-time probability distribution we are talking about right now, okay? So what you are asking is, what is the probability that the trajectories will have some value x1 at time t1 and x2 at time t2 and so on, okay? Or differently, what is the fraction of all trajectories which satisfy a certain constraint? And this constraint is that x of t1 equals t1 and x of t2 equals x2 and so on, okay? So given your probability distribution functional, this guy, okay, you can calculate this fraction, right? You can incorporate those constraints with there is a simple way to do it, right? If we assume that the x is discrete values, so we don't have to deal with Dirac deltas, that would be, so the probability that Tn xn, this would then be equal to integral. You would have delta x t1 x1 delta x tn xn x dx. So these are constraints, right? This is our distribution. When you integrate it like this, you reduce this probability distribution to standard normal multivariable probability distribution, multi-time probability distribution. Okay, but this is the master objects. The rest, everything else you get from it by calculating appropriate restriction or
Sophisticated way of assigning values to the function.
Oh, yes.
Integrating
Yes.
the delta function.
yes, but
I want to like F
But
And
there is
I write
there
it
is.
as f of x times delta x minus a, and I integrate over x.
But this
I
but
saw
look.
it when I was young, when Professor Wódkiewicz was giving
But look,
some
this has
seminars on stochastic
but this has consequences. Imagine now that we take this probability and marginalize it over any argument. So I take this guy and I sum it over xj, right? What happens then? Right? We enter with the sum here, we grab the delta and sum over it, and this turns delta into one, into identity. Right? And this guy is just equal to one. Agree?
Yes.
Even if it was, Dirac deltas, it still would work, but we don't want to do difficult stuff. But this is like, this will reproduce for us this multi-time probability distribution where TJ is struck out, right? Yeah. By definition. You see? Okay. And there is more. Because here we assume that our observable is described by, is a stochastic process, right? There is a trajectory picture for it. I mean, that you have this distribution on space of trajectories. But you can, you can think in a phenomenological way about it. From experiments, you would get those probabilities. This kind of probabilities, right? Like in our, this is our whole shebang. We're starting from those probabilities. And it turns out that if those probabilities are consistent, that is, if you sum over to get the shorter one, so this is called consistency condition. So if you have this,
the shorter one takes you much more space. You have to invent some new notation for this.
so if this master, the stochastic is the probability over over trajectories exists, you have those multi-time probabilities are consistent, but also this is so-called Kolmogorov extension theorem. If you have family of multi-time probabilities that are consistent, this implies that this stochastic process exists. So it's if and only if.
Some theorem which goes the opposite way.
Yes.
Here we assume that if we have stochastic process, then this consistency condition
is satisfied. Yes, but also
there is also the vice versa.
Yes.
If this condition for each of this.
Yes, for every multi-time probability from this family, marginalization produces a shorter one, and marginalization over every argument, not just the last one, everyone. It implies automatically that you have this stochastic process, you have this trajectory picture. In other words, the observation number 2 says that we violate consistency condition. So that's why it's called inconsistency, which means that this quantum observable.
Not general results.
Yes. Okay. In general, yeah. You can find
There are cases when
there are limits. There are cases where it will be satisfied. In general, it's not satisfied. Therefore, quantum observables, the things we are measuring right now, cannot be interpreted as a trajectory. So
this
this
are going much too far, because what we prove if we will find such situation, quantum mechanics, where this condition, this is not zero, then we might say, oh, that we violate.
okay.
But you didn't show that we can find it. Maybe classical world is imperfect.
I mean, no,
Yeah.
no. This is look, those probabilities came from experiments. Okay, we just checked if are there consistent.
From the lecture, come on. You said that we have this, and you showed that we can prove
But
that we
pretend
No,
that
you
it's
showed that when we sum over all results of the last blah blah, then we have zero, and you said, but generally it might be not. So we didn't show that it is not true. I would like you to give example where it is true, not true.
so just
Because we couldn't prove it, or it was not true.
take a qubit, do sequential measurement of 2 measurements on qubit, you will violate.
I was thinking in general term, not putting any physical word beyond all the symbols. I wanted to derive quantum mechanics from this somehow.
Take almost any quantum system, do sequential measurement on this quantum system, and you will find that you violate consistency condition. It's much more difficult to find quantum system for which you wouldn't violate this condition. It's very difficult. Sometimes it's possible. And in that case, you can say, okay, this is like classical. You will. Unless, okay.
I will take Gaussian state localized.
If there is no dynamics at all, you won't violate. If your system is completely static, okay, nothing changes, no evolution. It has Hamiltonian. You will violate the consistency conditions. Virtually all, that's why I call it, the general observation. Virtually all quantum systems violate consistency condition, which means that virtually in all cases, quantum systems are not classical. It is, because quantum mechanics is, it's a weird theory.
Free particle. You want to have discrete set of variables, yes? So you didn't say what observation is. What do you mean observation? Because I would like to take the Gaussian profile, that is 300 Hamiltonian.
If you want to remember how to,
and then it spreads, and then what is
do sequential measurements. Write down sequential measurements. Is there another one? There are formulas. You know the formulas. You know the formulas. No. We're trying to deduce formulas, but we are pretending we don't know, right? You remember your courses on quantum mechanics, right? You know the formula. We just on the break we just wrote the trace formula, right? We did.
So do you use this text or also I was lost because the first observation was about conditional probability. Yes.
No. What? Where conditional? It's not conditional.
It's false.
You are switching gears, because first of all, you said that we are going to derive phenomenological quantum mechanics. So derive quantum mechanics from phenomenology. And now we say that we know quantum mechanics, we know that there is trace, we know everything.
I thought, look,
I don't know
again, look. It is those probabilities. in principle could be obtained from real experiments. Okay, but I didn't do experiments. Obviously, I didn't do them.
Sure, so
So-
you have a sequence of.
So where did I got this stuff? Emilia asked that. Where did I got this stuff from?
I have serious problem with what you said, because you are using discrete set of observables. We are not talking about continuous variables.
No,
Then
yes.
it's very hard to me to find classical mechanics with discrete set of variables that I can, or quantum mechanics, which are corresponding classical variables. I can have spin or state, but then I assume quantum
Telegraph
from the
noise.
very beginning. For me, it would be position. And then I don't know how to do sequential
Yeah.
measurement and how to repeat measurement after the second
I mean,
measurement.
Of course, if you're talking about position is very
But this is what we have in classical mechanics. We don't use anything
no, not true, not true.
Generalized,
Telegraph noise is a discrete valued classical system.
What?
Telegraph noise.
oh,
There's nothing classical about continuous variables. It's just
nothing.
it's not special. Okay, it's nothing special about that. In classic,
Take a system, some particles, not some signal generated.
But-
Telegraph noises. So these are abstract numbers, 1 and 0, and take and measure.
Look.
I don't know how to repeat this on the real system which has Hamiltonian. Give me Hamiltonian for this telegraph noise.
okay, I could give you if you want to. There's no problem with that, but it's I don't know what the issue is here. I really don't understand this.
So maybe I can follow, because this first observation is fine, I would agree. Then a second observation somehow follows the first one, it's yes, inconsistency, as
Yeah,
I understand. Then you want to say, if there is a stochastic process behind the probabilities, this consistency exists.
Yes. So if there is no consistency, it means there is no stochastic process behind. Exactly. And I would add to that.
My problem is that you said we know that this is not true, and this is obvious for everybody who knows quantum mechanics. That's what you said, and I am confused. I don't know if it is not true. You said it is always not true.
Okay. Almost always. Almost
If
always.
If I remember quantum mechanics, or I can remember.
So look,
it is.
So pretend you don't know quantum mechanics. Role play you don't know. And I'm just telling you, this is what I mean, okay, I see you have a problem in like letting go what you know about quantum mechanics and just
Just say that we have a sequence of some results.
exactly.
There is a conditional probability for them.
Not conditional. Not conditional probability. No, it's you have joint probabilities.
Yes, but you have some sequence. And the order of time is very important.
Yeah, but this is joint it's not conditional probability. It's joint probability.
From the one.
Not follows, it's also similar. It follows. Follows would be
What she said is that we have this.
follows means implies, right? It's not implied by this. It's an additional data point.
Depend-
Well, it's not independent. It's the same theory we're talking about here, but it's not implied by the first one.
Found that this is something which is.
And then you want to
What's
say
going on?
that general what you have is
So we want to say that for this is more than probability theory.
Yes. Look, this means that what we are describing cannot be mapped onto a trajectory, like all other classical theories can. You cannot, because you violate the basic property of theories, which could be described in terms of stochastic processes.
But I'm talking about multi-time probability or multi-point probability or some joint probability.
Mhm.
First of all, let us take that we have joint probability distribution that are marginalized over the last variable, and we see that there is such property.
Yes.
Then we saw that if we marginalize it over with respect to any other, it is not true.
Yes.
But this was only theory in classical probability, not in quantum mechanics.
What? No. What?
Doesn't, yes,
That's
doesn't.
how we got it.
What?
That this
What is,
cannot be proven in general for general probability.
What do you mean? Proven?
Multi-point probability.
What do you mean?
Pardon?
What do you mean?
Look at the text here. I'm showing you the non-equality. And
Yeah.
how I understand that this cannot be proven. It is not true for general multi-point probability distribution.
Yeah. So for probability distribution, the described experiment that our student done.
No.
Yes. Yes.
We're not take literally what I am saying. You are
Oh,
adding some
okay.
words that I never said. Maybe I misunderstood, but I want you to take literally what I am saying.
Okay. Okay. So
This is the formula which you said that marginalization over
readouts.
readouts. But this is not, if I say this theory in another way, if I have left hand side, which is n-point probability distribution, if I any probability distribution, which is well defined n-point probability distribution. If
Okay,
I
good.
marginalize this any arbitrary
Mhm.
n-point probability distribution over any of
Yeah.
variables, this will be true or not?
If you just have some probability distribution in vacuum, just have.
Vacuum mathematics.
Yeah, I mean vacuum. I'm saying that you just have this one n variable probability distribution. You marginalize, you get some probability distribution that has one less argument. We're finishing. Don't worry. We have to finish. But you know, here we have a you know, those probabilities came from experiment.
Yeah, so I am, my question, are you adding physics to it or not?
Yes.
Okay, so you made a statement about physics here. And I missed
Yes.
it was statement about physics, right?
Yeah.
I said that it's a statement about
Look,
mathematics.
look. No. It's all the time physics. I don't. What's going on? Look, if this was a classical, if we measured classical systems, okay, not quantum systems, we would find observation 2 would say that they are consistent. Probabilities are consistent. We find out they are not consistent. They are inconsistent. Therefore, we are dealing with non-classical theory. We cannot describe it in terms of trajectory picture. Mhm. Yeah. Okay. All right. So we have to finish. So
Nice.
we will continue next week, hopefully. Maybe we will be able to clarify a bit what happened here. There was some confusion here, probably that was some failure of communication on my part. We'll try to do better next time, so stay tuned.